Hello everyone, welcome back to part 2 of chapter 28. In the last video we defined the magnetic field and magnetic force and saw how the two were related to each other. And we can do so in an equation that is similar to what we had for the electric force, which was just QE. But in the case of the magnetic force, the charge actually has to be moving through the magnetic field before we notice any of the effects of magnetic force. Now, since we have both of these expressions as forces, the next thing that we would want to do is see if we can combine the forces to produce a net force expression. And any forces can be added together using the appropriate vector map. But specifically, we want to see if it's possible to produce a net force of 0 in a given system. And that would mean that our two forces would have to be of equal and opposite magnitudes. Stylus isn't wanting to work properly. There we go. All right. So is it possible to have these two separate forces that are acting on the same charge of Q have equal and opposite force values? And the answer to that question comes from a device that we call the crossed fields device, or the Thomson apparatus. And this was a device produced by J.J. Thomson, who figured out what the orientation was between not only the electric and magnetic forces that were acting on a charged particle, but also how the magnetic and electric field lines needed to be oriented in that given system. And so what we're going to do is we're going to build ourselves one of these cross fields devices. The first thing that we're going to do is we need a source of charged particles. And usually you can accomplish that just by having a large amount of energy passing through a conductor to the point that the conducting material itself is heated up to a very high temperature, and because of those high energy values associated with those high temperatures, that material can no longer hold on to certain atoms or particles, and a lot of those energetic particles are thrown off as ions or charged particles, which is exactly what we need. So we're going to do that in this fashion. We're going to take something like a filament. If you look inside of an incandescent light bulb, you'll see a very tightly wound coil. And those tightly wound coils, even though they look really small, if we were to stretch them out, a lot of those filaments can have upwards of 1 to 3 meters worth of wire. And they have an extremely small cross section, which means these filaments have a very high resistance value. And if we hook that filament up to some kind of EMF source, that filament is going to get very, very hot, and it's going to start spitting off charged particles. Now, these charged particles, as they're spit off of the filament, they're going to go in whatever direction they feel like it. We're going to have a random distribution of these charges. But we need some means of controlling the direction that these charges are traveling, because at some point I'm going to have to know what direction is that charge traveling. I need some information about the velocity of that particle. Now let's say I want particles that only travel in this given direction. So how do I filter out all the other particles that are bouncing around in the system? Well, one way to do that, and a really easy way to do that, is to set up a partition in the device. And that partition will have a very small hole, or just a little pin hole right in line with where we want those charged particles to travel. And then that partition will prevent any other particles with any other velocity from continuing forward. Now these particles might rebound, that's okay, but we just want the ones that are going to travel directly through. And we'll highlight that direction here with green. So we'll say we only want these charges right here. Something else that's really going to help is if we put this entire device inside of a vacuum. And the reason we want to do that is because these charged particles, because they're charged, they're going to be far more likely to want to interact with other things around them. And there are plenty of molecules in air that these ions could interact with. And so if we just pump all of the air out of the system, so we're going to turn this whole system into a vacuum, that will prevent our charged particles from interacting or colliding with anything else in the system. I'm going to go ahead and box in this back portion here because we want to keep all of those random charged particles from progressing forward. We only want the ones that are traveling along that straight line to make it through the partition. And so now we've controlled the direction that our charged particle is traveling. The next thing we want to do is we want to expose these charged particles to an electric field. And that electric field will in turn produce an electric force that will act on the charges. To do this, we're just going to use a capacitor. So here we have the plates of a parallel plate capacitor. We will connect the plates of this parallel plate capacitor to another EMF somewhere in the system. Maybe it's over here somewhere. We'll call this EMF2, and this can be EMF1 because the voltage sources of these two EMFs may not be the same. In fact, we're probably going to need a pretty large voltage source to produce our charged particles, whereas the capacitor that we set up won't need as strong of an EMF. But we hook up the EMF, we get a collection of charge that builds up on the what we call positive and negative plates of the capacitor. And these are the charge values of the capacitor plates. Those are going to be separate from the individual charge that is moving through the system. So I'm going to call this Q0, just because this is going to act as a test charge that moves through that capacitor system. And I've been labeling all of these charges as positive charges, but they could just as likely be negative charges as well. We'll consider the positive charge scenario, and then if we need to, we can switch over to the negative charge scenario. But now that my capacitor plates are charged up, the capacitor will be producing some electric field lines. Those electric field lines will point from the positive plate to the negative plate. And just for this discussion, we'll assume that those field lines are uniform. And so now I have my charged particle of Q naught. Move that right up there. I have my charged particle of Q naught, which is going to enter this region of electric field that is pointing down. Our equation for electric field says that electric force equals Q times electric field. Because our charge is positive, then the electric force will have to point in the same direction as what the electric field is pointing. So I'm going to use, what color should we use here? I guess we can use purple. So this is going to result in an electric force that pushes down on this charged particle as it tries to move through that capacitor plate. As that force pushes down on the particle will deviate from its path and quite possibly end up crashing into the bottom plate of the capacitor. Or if it's moving fast enough, it may just deviate and then get spit out the other end, but still we're going to see a deviation in the path of that particle. What we want to do is prevent that from happening. We don't want our charged particle to deviate from its current path as it travels through the capacitor. And the only way that that could happen is if we have some kind of counterforce, which will counteract the electric force in the system. So let's see what color I want to use this time. I guess we could use blue. So we need a counterforce, which will be in the form of a magnetic force. But we know that the only way for a magnetic force to be produced is if there is a magnetic field present for our charged particle to move through. Well, this just became a pretty straightforward problem, believe it or not. We have our expression for magnetic force that says that the charge of our particle times the cross product of our velocity and field vector will produce the magnetic force vector. We can already see the direction that that magnetic force vector needs to be pointing. It needs to be pointing straight up. So we know the direction that that force has to point. We also know the direction that we want our charged particle to be traveling in. We want it to consistently move to the right. So we know the direction of the velocity for that charged particle. The only piece of information that we don't know is the direction that the magnetic field needs to point. So let's go back to what we learned in the previous video about using the right hand rule. So we do need to use the right hand in order for this to work. And the respective vectors of our cross product. The first vector in the actual cross product is the velocity, and that is the index finger. Second vector in the cross product is the magnetic field vector. That is going to be our middle finger. And well, why wasn't this the first vector? And that's because this is the result, or the resultant of the cross product method. If we take our thumb and we point our thumb up in the direction that the magnetic force has to point, and if we point our index finger to the right, which is the direction that our charged particle has its velocity pointing, and then we extend our middle finger, the only way that we can actually point our middle finger and not break anything is if our middle finger points into the screen. And so our magnetic field will have to point into the screen. This is the only orientation of magnetic field that will result in our positively charged particle experiencing a magnetic force that points up. And we have to have our magnetic force point up because we need our two forces to be pointing in opposite directions so that when they add together, we can get that net force of 0. Okay, so we have the necessary direction of the magnetic field figured out. So how much magnetic field are we going to need? Essentially, we're coming up with the desired vector for the magnetic field. And every vector has two pieces of information, magnitude and direction. Well, we've already found the direction part. The magnetic field has to point into the page or into the screen, hence the circle with the X in it. This indicates a vector that points into the page. But now we need to figure out what the magnitude of this magnetic field is going to be. And this is pretty straightforward as well. We already know that the magnitudes of these two forces will have to equal each other. So let's take those two expressions. They're right up here. Let's set them equal to each other. Our electric force is QE. Our magnetic force is QV cross B. We have the same charge on either side of the expression. This is what we were calling our test charge earlier. But now that that test charge value is factoring out of either side of the expression, we really don't need to know what the charge is. And this is important because our test charge, well, now that it's factored out of both sides of the expression, it could have been positive or negative. It really doesn't matter what kind of charge we feed into this apparatus. It could be positive or negative, but the resulting direction of our magnetic field will still have to be pointing into the page. And you can actually prove that to yourself if you fire an electron through this system. You'll just have to go through and redo the math. Essentially, putting a minus sign in front of everything as you go. But if you put a minus sign in front of everything, that minus sign is just going to cancel out at the end anyways. That means we're left with this expression. And if I want to know what the magnitude of the magnetic field needs to be, well, let's take that cross product and let's evaluate it. We have the magnitude of each vector times the sine of the angle between them. But what is the angle between our velocity vector and the necessary magnetic field vector that we just discovered? Our velocity is pointing to the right. The magnetic field is pointing into the page. That's a 90-degree relationship between the two. Sine of 90 is 1. And we now have the magnetic field magnitude equal to the magnitude of the electric field divided by the magnitude of the velocity. Or, another way that we could write that is that in order for our charged particle to pass through this system that includes both electric and magnetic fields, we're actually going to overlay the electric and magnetic fields together. It's not going to be one after the other. So I'll go ahead and draw that magnetic field right here. Oops. Gotta turn the eraser function off. So we have both our electric and magnetic fields acting on the charged particle together at the same place at the same time. If we want that charged particle to pass through the device completely unhindered with a constant velocity, well, constant velocity means what? Net force of 0. There it is. But that also means that there has to be a certain ratio of electric field to magnetic field magnitudes in order to achieve that constant velocity. And that right there is the ratio that we need to have. Now, in most cases, the velocity of the charged particle is probably not going to be something that we can control in a laboratory setting, because those charged particles are going to be spit off of that filament, and that the velocity of those particles will probably be somewhat consistent in terms of their magnitude, but different energies, different particles, they're going to have different velocities. But that means that we can measure the velocity of those particles by tweaking the values of the electric and the magnetic fields. And these are things that we will be able to control in a laboratory setting. The electric field can be controlled by controlling the amount of charge that we deposit onto those capacitor plates. We're going to talk more in this chapter and the next chapter about how we can produce magnetic fields and control the magnitude and direction of those magnetic fields. But another benefit to this Thomson apparatus, I'll go ahead and redraw a portion of the system here. So let's say we have our charged plates of our capacitor, and those charged plates are producing electric field lines. If we choose not to use the magnetic field, then these charged particles that are entering the capacitor, we said that they were going to veer off. When they enter the system, they're going to veer off and most likely crash into the capacitor plate. Well, if all of these particles have basically the same velocity, why would they crash at different locations? I've got 3 different crash sites here for these charged particles. And again, we're just considering the electric force right now. But keep in mind that any force is going to result in an acceleration of a particular mass. If we're applying the same force to different masses, then those different masses are going to accelerate at different rates. And that means that the first particles that collide onto our capacitor plate are going to be the particles of the smallest mass, because they are the easiest to move. Whereas the particles on the far end, those are going to be the largest particles in the system. The larger the mass, the harder it is to move. And then we'll have some medium-sized particles along the way. We basically have an atomic filter system here. There are plenty of ions and molecules that may have the same charge value, but they're going to have different masses. And this provides us with a very straightforward method of filtering out those different particles from one another. And so what we could do is we could put some kind of a collection bin at these locations, which we could calculate the location of where these individual particles are going to eventually deviate. And we can collect charged particles of different values and then use those particles for future experiments. Now, the next topic that we have for this chapter. So this cross fields device is important in seeing how the electric and the magnetic fields behave together naturally. If we want those forces to equal out and allow our charged particles to move unhindered, then there has to be that very specific orientation between the electric and the magnetic fields out in space. And that orientation, as we can see now from our picture, that orientation has to be perpendicular. This is the only way that we're going to be able to have charged particles move through a system in a straight line, is if these two fields are perpendicular and if they carry the appropriate ratio that we saw down below when we balanced out those two force equations. All right, moving on. The next thing we want to talk about is if I have some charged particles that are moving through a conductor. So now our charged particles have graduated to becoming current. So we have charged particles that are going to be moving through a wire. And so we'll say we have our charged particles moving through a wire. So up is the velocity of our individual charges, but the flow of positive charge is called current. So the direction of our current, even though current is not considered to be a vector, the direction of our current flow can be used as a substitute for the direction of where our individual charged particles are moving. Now, these charged particles, they're flowing up through this conducting material, but as they flow upwards, I am going to apply a magnetic field to this wire. And that magnetic field, I'm going to apply it so that it points into the board. And it's typical to see multiple renditions of these vector notations of in and out of the board, just to drive home the point that this entire wire is being saturated by these magnetic field lines that are pointing into the page. As these charged particles move through that magnetic field, there will be a magnetic force that these charged particles experience. The first vector in the cross product is velocity, And so we take our index finger, we point in the direction of the velocity. So your index finger should be pointing up in the direction of the current. The second vector in the cross product is our magnetic field. So keeping your index finger pointing in the direction of the current. Our middle finger now needs to point into the page. And then we have the resultant vector, which is what we're looking for. Resultant vector is thumb, and the only direction that you can point your thumb in is to the left. So there will be a magnetic force which is tugging on these charged particles, pulling them to the left. Well, that means these charged particles are going to deviate from their current path, and eventually they're going to slam into the side of the wire, and that magnetic force vector is going to pin them in place. And we're going to see multiple positive charges that get pinned up against the side of the wire. As this is happening, what if there are any negative charges in this wire? Well, negative charges, as we've seen, we can actually see what the effects would be if I plugged in a negative charge value for Q. What would happen to the overall direction of our force vector? Well, it would just turn around. It would flip over. And that means we will see all of the negative charges in the wire get pushed over to the right-hand side. The inside of our wire is starting to look a lot like the plates of a capacitor. In fact, the two side walls of the wire are going to start producing electric field lines, just like what we would have in a capacitor. Those electric field lines are going to want to produce electric forces. And the electric force that acts on those positively charged particles, well, those are going to point to the right. Sorry, wrong subscript there. Should be F of E. And the reason we're going to see electric forces pointing to the right is because that's the direction that our electric field is pointing. So what's really happening here? Well, if I start with a wire that has no current running through it, there are no charges to be pinned up against the side walls of this wire. And we had the magnetic field lines that were going into the board. So no current means no charge flow, means no magnetic force to pin charges up against the walls. Without having the magnetic force to pin the charges up against the side walls, we won't have a concentration of charges building up on the side walls to produce those electric field lines. And without the electric field lines, we won't have the ability to produce the electric forces. Look at the directions that magnetic force and electric force are pointing. Eventually, there's going to come a point where these two forces reach that equal and opposite relationship that we saw in the Thomson apparatus. And so we come to another realization that these charged particles, whatever they are, there's going to be that relationship of electric field to magnetic field ratio that will allow us to measure how fast the charges are traveling through our wire. Once this occurs, once we reach this equilibrium between the magnetic force and the electric force, that's when our charged particles regain their ability to travel through the wire unhindered. It's only the first few million or so charges, maybe billion, that enter the wire that end up getting slammed up against the side walls of the wire. But once our electric field and electric force reach a high enough magnitude to balance out the magnetic force, those charged particles will just continue traveling through the wire exactly as they were intended to. And we can use this information now to tell us how fast those charged particles needed to be moving. Well, then what? After we've got these charged particles pinned up against the side walls, how does that help us? Well, for most conducting materials, we're probably not going to have both positive and negative charges traveling through the wire at the same time. More likely, we're just going to have electrons. And those electrons are going to be negatively charged. But that's not to say that it's entirely impossible to have positive charges moving through your wire. If you only had one type of charge passing through your wire, you would never actually be able to achieve this balance. And you would have a net force tugging your wire in one direction or another. And simply by knowing the direction that the wire is being forced into, you would be able to know the sign on the charge carriers that are passing through your wire. So we would know if we were in fact using electrons or positrons or protons or just about any other kind of material. And that means that the velocity that was just measured can be used as a substitute for the drift velocity that was discussed in one of our previous chapters. The drift velocity measured how quickly these individual charges pass through the wire. So our charged particle, whatever it is that happens to be traveling through this wire, we can set that equal to the test charge of Q naught. So whether it's a proton or an electron, at this point it really doesn't matter, because that drift velocity is now going to be the ratio of our two fields. And we know back in chapter, I want to say this was 26, our drift velocity could also be measured as the current density J divided by NE, where N was the number charge carrier of the material. This was a property of the material that told us essentially how many free charges were available to be moved through the system. But if we take that information, again, the magnetic and electric fields are going to be things that we can control. The current density is something that we can fairly easily measure. It's going to be the amount of current per cross-sectional area. So A is the cross-sectional area of the wire. That's something that we can measure. We can measure the current fairly easy with a multimeter. And then E, that was the elementary charge value associated with the charges that were moving through the system. So this means that with a quick adjustment, we have N equal to BA. Current density was I over A, and then we still have E there. Is that right? And so we can measure that material property. We can measure how many available charges are in a given conducting material. This was per unit volume, I should mention. N was the number of charge carriers per unit volume. So our wire would be made of some kind of material. There would be a volume associated with this wire. It would be the cross-sectional area times the length of the wire. So cross-sectional area times length. Sorry, that's incorrect. Little n equals big N divided by the volume, which is cross-sectional area. Okay, so I think I'll just leave it at that for right now. So it is possible to take some fairly easy measures in a lab and get the number charge carrier of a given material. So whether it's copper, gold, silver, aluminum, any kind of conducting material will have its own unique number charge carrier value. And then if you would prefer not to work with the electric field itself, one of the reasons why we started working with the electric potential was that it's a lot easier to work with electric potential as opposed to trying to measure electric field. We can measure electric potential quite easily, again using a multimeter. And back in chapter 24, we found that the electric field produced by a potential difference over a given displacement, which in our case would be the length of the wire, could then be plugged in and let me see here. Oops, I've got my, that's a big mistake. I had my drift velocity ratio upside down. That would not have been good. But this means we can replace E in our expression with a more easily measurable value of voltage, length of wire, and E, the elementary charge. Okay, so I'll leave it at that. We don't really need to take this any further. I'm just double checking my notes here to make sure that I got everything in the right spot. NAL. I think so. I've got, I think my cross-sectional area was supposed to cancel out at some point. Not sure what happened there. I'll have to go back and check my my derivation here, but I don't want to take up any more time on the video here. I was supposed to have factored out the cross-sectional area at some point along the way, and I failed to do that. But this is the final expression that we have. But this just goes to show you there's lots of different ways of measuring the same value with different terms and different substitutions. The method that you choose should be based off of what is easiest and most efficient for you to measure. And if that means that you're measuring all of these values in a laboratory setting, so be it. You want an expression that's got terms in it that's very easy for you to measure. Otherwise, if these are things that can be looked up in a standardized table somewhere, even better. Go ahead and look those values up. Okay, so that brings us to the end of what I wanted to show for this video. We have a few more things that we need to cover for this chapter. Basically, what we need to do is we need to figure out what's going to happen to these charged particles after we pass them through a region of magnetic field. Well, we already kind of know that. We have a charged particle. It's going to enter a region with a magnetic field. And based on our cross product, FB equals QV cross B. Oops. We know that if this charged particle enters that region, it will experience a magnetic force that points up. So use the right hand rule. You've got your magnetic field pointing into the board. That's your middle finger. Velocity is your index finger. Resulting force is your thumb. Well, if I have a force that's pointing up, then we're going to see this charged particle deviate its path. Let's use a different color for that. We're going to see our charged particle deviate its path. But how long will that particle continue to deviate its path? Well, as long as it remains inside that magnetic field. So let's consider a slightly larger magnetic field region. So all of these are just field lines for our magnetic field. If we allow our charged particle to enter this field, the moment it enters the field is the moment when we see that magnetic force start pushing up on that charged particle. And that means the charged particle is going to begin deviating its path. But now the direction of the velocity vector has changed. If the direction of the velocity vector changes, what is going to happen to the resulting magnetic force? Well, it's going to have to change as well. As this charged particle starts to curve upward in its path, the magnetic force that results is going to have to change direction in such a way that it can maintain the necessary perpendicular relationship. Remember that any resulting vector of a cross product has to be perpendicular to the original two. But if my force vector changes its orientation, then that's going to cause the charged particle to deviate in its path even more. The end result of this is going to be that our charged particle will start orbiting in a circle around these established magnetic field lines. And there will be a radius associated with the orbit of that charged particle. This has just turned into a Physics 1 problem. We have a magnetic force which is constantly pointing towards the center of this circular path. And the reason our magnetic force is changing direction is because that magnetic force is constantly changing the direction of the velocity. As the velocity changes direction, the magnetic force has to change direction. So these two are constantly affecting one another. The force changes the direction of the velocity. In turn, the velocity changes the direction of the force. And this just keeps happening again and again and again, causing our charged particle to travel in a circle. This means that we can relate the magnetic force to a centripetal force. And back in Physics 1, any force could be represented as mass times acceleration. But in the case of a centripetal acceleration, also known as the center-seeking acceleration, so we're going to have acceleration towards the center of the circle at all times, at all locations. And this could be expressed as the speed squared divided by the radius. So here v is the magnitude of the velocity. It is not the potential. It is not voltage. This means that we can set our magnetic force magnitude equal to the magnitude of the centripetal force. Well, we already have that. QV cross B. That's our magnetic force. At all times, traveling around this circle, the velocity vector, our velocity vector is constantly changing as we go around in a circle, but how does the velocity vector at any point compare to that of any of our magnetic field vectors? Our magnetic field vectors are always pointing into the page. Even though our charged particle is moving around in a circle, our velocity vector and magnetic field vector are always at a right angle with respect to each other. That makes evaluating our cross product very straightforward. We now have sine of 90, which is 1. We have QVB for the magnitude of our magnetic force, and that equals the centripetal force expression from Physics 1. We have the same velocity on either side of the expression. In this case, we have velocity to the first power. Over here, we have velocity to the second power. So we'll cancel that out. And now we have a relationship of charge to mass. Let's see here. We have V over BR. We have a charge to mass ratio that tells us what the velocity and respective radius of the particle need to be. So let's try a very quick example problem, and then we'll call it good for this video. If we have a proton with a velocity of 10 to the 6th meters per second, and it enters a region where the magnetic field is half a Tesla oriented into the page, what will be the radius of the orbit that that proton adopts? So this proton is entering a region where the magnetic field lines are into the page. So just like the picture that we saw up above. That charged particle will adopt a circular path for its motion, and for all purposes, it's going to be trapped there forever until some other force comes along and allows that charged particle to leave that orbital path. Well, if we want to know the radius of this orbit, let's take what we have, let's rearrange for r. R will have to equal V over B times M over Q. Got all that right? And we have numbers for all of this. We know our velocity is 10 to the 6th. We can look up the mass of a proton. Every proton in the universe has to have the same mass as every other proton in the universe. And so we'll go ahead and Google that value. Mass of proton. And that's coming out to be 1.67 times 10 to the negative 27 over the magnitude of our magnetic field, which is half a Tesla, 0.5, times the charge of our proton. But the proton carries an elementary charge value of 1.602, 10 to the minus 19. All of that gets plugged into our calculator. So I'll go ahead and open my calculator app here. We have 1.67 times 10 to the minus 27 times 10 to the positive 6. So that would be the same as taking 10 to the negative 21. And then we divide by 0.5 and divide by 1.602, 10 to the negative 19. Oops, and I got some kind of syntax error here. I have to try this again. 1.67, 10 to the negative 27 times 10 to the 6th divided by 0.5 divided by 1.602. All right, so I am getting 0.021. And so that should be in meters. And so this proton, as it enters this magnetic field region, will start orbiting in a circle that has a radius of about 2 centimeters, or roughly 4 centimeters in diameter. We can then take that expression of the mass to charge ratio, velocity, magnetic field, radius, and we can ask questions about period of motion, which would be, let's see here, velocity is displacement over time. We would have a displacement equal to the circumference of the circle. And then the time required to complete one complete orbit, that is the period of motion that we're talking about. And so that means that the period of motion would be 2 pi r divided by v. We can rearrange our expression to solve for v and then plug that in to the period expression. We have 2 pi r divided by the expression for v, which is qb r divided by m, so m is going to come up top there. But interesting part is that we lose the information about the radius of the orbit. Turns out that the size of the orbit doesn't matter with respect to the period of motion. And then the final step that we can take is, now that we know how much time it's going to take for one rotation, so in other words, this is the time required for one complete event, If we invert that value, then we get what is known as the frequency. And the frequency tells us how frequent an event happens with respect to 1 second. So in the case of period of motion, we have units of seconds. In the case of frequency, we have inverse seconds or hertz. And this is a really big deal when it comes to things like charged particles getting captured by magnetic field lines, which is the reason why we have things like northern lights, aurora borealis, and things like that. We have charged particles from outer space, in particular the sun, that get trapped on the magnetic field lines that the Earth is producing. Those charged particles then wind their way around the magnetic field lines until they slam into the upper atmosphere at either the upper or, at either the north or the south pole. And when those charged particles interact with the upper atmosphere, they release their energy in the form of a very beautiful light show. So I would recommend you look up some videos of aurora borealis, and the different colors of light are specific to the different energies of the different particles. So it's a very, very beautiful side effect of nature, but it's all explained right here by the physics and the motion of charged particles as they pass through a magnetic field. So that brings us to the end of video 2. We'll talk some more about these charged particles in the next video. We'll see you then.